Hey everyone, welcome. Today, we're going to pull back the curtain on the incredible world of amateur radio. I'm talking about a community that spans the entire globe, all powered by pure tech. We're going to break down how it all works, right from the plug in your wall to hearing a voice from the other side of the planet. So let's jump right in. So, have you ever really thought about it? How can you possibly talk to someone across an ocean without the internet? No cell towers, nothing. I mean, it sounds like straight up magic, right? Well, today we're going to show you it's not magic. We're going to break down the science and the real-world steps that make it happen. All right, here's the plan. First, we'll nail down the basics: power, wire, and safety. Super important. Then we'll dive into antennas, which is where the real fun starts. After that, we'll talk about fighting off all that static and noise. And finally, the grand finale, making that global contact. All right, section 1, power, wire, and safety. Look, before you even think about hitting that transmit button, you've got to get the power situation right. Because if you get this wrong, you're not just risking a little bit of static, you could literally fry thousands of dollars worth of gear, or even worse. So yeah, let's make sure that doesn't happen. Okay, I want you to burn this number into your brain. 10.5 volts. It doesn't sound very dramatic, I know. But if you're ever running your radio off a typical 12-volt battery, like in an emergency or for portable operations, this number is everything. It's the razor-thin line between a healthy, long-lasting battery and a very expensive brick. So what's so special about 10.5? It's because of this. If you let a standard lead-acid battery drop below 10.5 volts, you're basically damaging it on a chemical level. You're killing its ability to ever hold a full charge again. So for anyone who depends on battery power, think of 10.5 as the absolute do-not-cross line. Seriously. Okay, so that's batteries. But what about plugging into the wall at home? The same idea of safety is just as critical, maybe even more so. The National Electrical Code is super clear on this, and it's not a suggestion, it's a rule to prevent fires. For a 20-amp circuit, which is pretty common, you have to use wire that's at least number 12 gauge, or thicker. It seems like a tiny detail, but it's one that can prevent a total disaster. And speaking of disasters, let's talk about the big one, the one that every radio operator respects and fears: lightning. I mean, you've basically got a big metal rod sticking up in the air. It's a perfect target, so you have to be ready. The key to safety here is something called bonding. It's where you tie all your ground wires, from your equipment, your house, everything, together into one single system. This gives a lightning strike a super easy, safe path to the earth, instead of letting it jump around and, turn your radio room into a pile of ash. Okay, on to section 2, your antenna and you. So, our power is safe, it's stable. Now for the exciting part, turning that electricity into a signal that can circle the globe. Your antenna is that magical bridge between the box on your desk and, the rest of the world. And trust me, this is where things get really cool. First things first, though, we have to understand a concept called SWR. That's standing wave ratio. Think of it like this. You shout into a canyon. You want your voice to travel out, right? But if a really loud echo comes bouncing right back at you, it messes everything up. You can't even hear yourself think. That echo, that's exactly what a high SWR is. It's your own power getting reflected back down the feed line from the antenna. It not only kills your signal, it can actually destroy the guts of your radio. So the goal is always to get that SWR as low as possible, to get rid of that echo. And this isn't just some theory you read about in a book. No, operators are constantly watching their SWR with a tool called a directional wattmeter. It shows you how much power is going forward out to the antenna and how much is being reflected back. It's basically a real-time health gauge for your entire antenna system. It's an absolutely essential piece of kit. You just don't operate without one. Now, when we talk about antennas, it's not a one-size-fits-all deal. There's a huge variety out there. So on one hand, you've got something like the classic dipole antenna. It's simple, it's effective, but how well it works really depends on how you set it up. Then, on the other extreme, you've got something wild, like a screwdriver antenna. This thing is a piece of engineering art. It has a motor inside that actually changes the antenna's length, so you can tune it perfectly for any band you want to use. It just goes to show you the amazing creativity in this hobby. Okay, section 3. Let's go inside the magic box. So we've got power coming in, we've got an antenna to send signals out. Now let's look at the brain of the whole operation, the transceiver. This is the heart and soul of your station. This is where your voice gets turned into a radio wave.
See, your radio is a delicate piece of electronics. It needs a very specific kind of power to work: smooth, steady direct current, or DC. But the power coming out of your wall socket, that's alternating current, AC, and it's jumping all over the place. So you need a translator. And that translator is called a full-wave rectifier. It takes that wild, messy AC power and perfectly converts it into the clean DC that all the sensitive circuits inside your radio need to survive. And inside that box, you've basically got two families of circuits working together. You've got analog circuits, which are kind of like a volume knob, smooth and continuous. And then you have digital circuits, which are more like a light switch. They're either on or off, ones and zeros. Modern radios are a beautiful blend of both. They use digital circuits, like CMOS, to be super efficient and save a ton of power. So with all this complicated stuff going on inside, you'd think it would be a nightmare to operate, right? Well, actually, it's way simpler than you'd imagine. Let's take something called the automatic level control, or ALC. It's a really clever circuit that basically makes sure your voice doesn't sound distorted or splattery when you transmit, but you don't need to be an engineer to use it. You control that whole complex system with just one simple knob on the front of your radio, your microphone gain. That's it. It's just smart, user-friendly design. Section 4. Okay, let's talk about the constant battle, the war on noise. You could have a 1,000-watt blowtorch of a radio, but if your signal is buried under a mountain of static, you might as well be whispering. It's completely useless. For every ham radio operator, fighting noise and interference is a battle you wage every single day.
Now, one of the weirdest kinds of interference is something called intermodulation. It's a bizarre phenomenon where two totally separate, strong signals can actually mix together, not in a radio, but in the environment, and create a new phantom signal that pops up right where you're trying to listen. And get this, the thing causing it could be something as mundane as a rusty bolt on a metal fence nearby. Seriously, hams even have a name for it: rusty bolt syndrome. So, how on earth do you fight a ghost signal caused by a rusty bolt? Well, you use some clever electronic tricks. Most modern radios have a circuit called a noise blanker. It's designed to listen for sharp, repetitive pops and clicks, like the static from a car's ignition, and it just zaps them out of existence before you even hear them. This tech is so good, it was even used back in the Cold War to fight against this infamous Soviet over-the-horizon radar signal that sounded like a woodpecker and drove operators crazy. The noise blanker was the weapon of choice.
And that brings us to the grand finale, Section 5, making global contact. We've got our power sorted, our antennas tuned, we're fighting off the noise. Now it's finally time to do what this is all about: talk to the world. So let's look at how it's actually done.
Okay, first things first. You'll hear this all the time. The very first thing two operators often do is give each other a signal report. Why? It's not just about being polite. It's critical data. By telling someone how clearly you're hearing them, you're giving them instant feedback they can use to maybe adjust their antenna or change their power to make the connection better. It's all about adapting to the conditions in real time. But hey, it's not all about voice. You can also send text messages over the radio, kind of like texting, using digital modes. One of the most popular is called PSK1. It is incredibly efficient. It can punch through terrible noise when you can't even hear a voice. And its secret weapon is something called VAR code. Just like Morse code gives shorter patterns to common letters, VAR code does the same thing for digital text, which makes it super robust, even for really, really weak signals. And the digital magic doesn't end there. There are systems like WinLink that let you send and receive actual emails with attachments completely over the radio. Think about how huge that is in an emergency when the internet is totally out. The special stations that act as the bridge between the radio waves and the internet are called gateways. It's just an amazing example of how flexible this technology is.
So there you have it. We've gone from a simple battery all the way to a global conversation. We've looked at the power, the safety, the antennas, the radio itself, and how to make that final connection. You've now seen the basic building blocks, the science, and the techniques. The rest is just about imagination. So the only question I have for you is, when you get on the air, who are you going to talk to first?